thank you, Alan, and all your colleagues, and the Wright Foundation, Monsieur Patry, and the Wright family for this wonderful opportunity. I can't imagine how privileged we've been, all of us, to have enjoyed this time here in Geneva. And thank you very much for making it such a wonderful time. I hope we can reciprocate with the science that we share with you. And as Alan has said, I'm going to talk about organic electronic materials, and the title is in front of you, and the reason for that will be clear at the end of my talk. And I pressed the wrong button already. I think Rod had that problem. So, one of the things that happened when we went back to Australia was that the University of Melbourne built a wonderful institute, a biotechnology institute, but they allowed a few organic chemists in as well. And of course, it's very attractive to be able to collaborate so strongly with biologists. And you see we have a breakout area and an atrium, and it is lit with inorganic LEDs. I hope one day that will be organic LEDs, as you will hear. And here we are taking some delivery of our equipment in that institute. So I'm going to talk about conducting polymers, about plastic electronics, about luminescence and polymer LEDs. I already mentioned LEDs. And then solar cells and how we might print solar cells as a cheap form of renewable light harvesting. So the story starts in 1954. And before I had anything to do with Cambridge University, Alan was probably well established there already. And the tradition was to take a photograph of the chemistry department. And here you see the chemistry department in the old building in Cambridge. And I want to focus on this one individual here. And let's look at him a little bit more closely. He's quite handsome, isn't he? With his flat top of the 50s. And here he is in the year 2000, right there. And this was taken in July 2000. And I think the person who took this photograph was well connected with the Nobel Committee, because this was a conference on synthetic metals, which these three gentlemen started, because in 2000, in October 2000, they won the prize for chemistry, for the discovery of conducting polymers. Alan Heeger, now at Santa Barbara, Alan McDiarmid, then at the University of Pennsylvania, and Hideshi Shirakawa, I think one of the first Japanese Nobel Prize winners, and many have followed since. So Alan McDiarmid was a New Zealander. Sadly, he died recently, but he was a great friend of the Southern Hemisphere, although he did all his work in Pennsylvania that won the Nobel Prize. And here he is at the University of Wollongong showing Alfred Nobel. And here, always at every conference, being a New Zealander, he would dance the haka, the New Zealand traditional Maori dance. And it didn't take much to get Alan McDiarmid, a lovely man, to do this. Now, what they discovered was that plastics, which we always think of as insulators, and I'm going to try and pull a cable up here without destroying the intricate wiring system, but we think of plastics as insulators. I can't get one up high enough. Here we go, that'll do. As to prevent us getting an electric shock. And what these three gentlemen discovered was that certain kinds of plastic, conjugated polymers, could be made to conduct electricity as well as copper. So this was a real paradigm shift, and clearly was worthy of the award of a Nobel Prize. The field exploded, and every large chemical company had an advanced materials research institute developing conducting polymers. But as is often the case, the first people were too early, and the polymers they worked with were too unstable to be used in commercial applications. So I'm going to talk about the next phase of conducting polymers when they were used as semiconductors rather than conductors. So used to mimic the properties of materials like crystalline silicon. And I'm going to focus just on, this is a huge field now, I'm going to focus on two aspects: organic LEDs with polymers and solar cells with polymers. But this is, has a wide range of applications, as you can see on this slide. And it's wonderful to have these business plan projections by commercial organizations, but this organization, which is concerned with predicting, amongst other things, the market in plastic electronics, shows it's really good for a grant proposal that even in 2012 they're predicting that the organic light-emitting display market will be about 1 to 2 billion, and even the solar cell market will be quite significant. And look where we will be in 2000, which of course is the European target, 20% of renewable energy by 2020. So, and it'll have to use the technologies we're going to talk about if we're going to make those targets. So it's an attractive area. It really has promise, but the promise has not yet been delivered in the marketplace, except in light-emitting displays. Now, I'm going to talk about the phenomenon of luminescence. One more slide, and then. So this is a little bit technical, but I want to explain that most organic molecules that can be excited by light, and that's that arrow, photoexcitation by a photon, can be lifted to the electronic excited state, and then normally they can relax to the ground state and give out light. Sometimes they relax by giving out heat, but typically photoexcitation is followed by release of a photon, and we call that phenomenon fluorescence. We can also make organic molecules fluoresce by exciting them by other means, for example, by a chemical reaction in which the chemical energy is transferred as electronic excitation energy to excite the molecule, and then it can give out the energy as light. And that is called chemiluminescence, and I'm going to demonstrate that in a minute. And Emil White defined chemiluminescence as the production of black body irradiation, of light in excess of black body irradiation by a chemical reaction. So in a sense, chemical reaction excites the molecule and it fluoresces and gives out light. So I've been very fortunate here in Geneva to have been introduced to Monsieur Rolf Obrichs, who's going to help me demonstrate chemiluminescence in a real experiment. But I want to talk about what I'm going to demonstrate on this slide first. And this is a very famous molecule in chemiluminescence, and it's used in biology as a probe, because if you can probe the behavior of luminescence in a body, then you can see what other aspects of the environment can change the luminescence. And so you can get a lot of understanding about proximity of materials by seeing how the luminescence changes in a biological experiment. And luminol is used for that. So this is the molecule luminol. And if you're not a chemist, then relax for a minute. If you are a chemist, then luminol will react in the presence of sodium hydroxide and water to give an anionic species which can be oxidized with hydrogen peroxide and potassium ferricyanide. So we're going to oxidize this molecule, and essentially we're going to turn those N-N bond into N-triple bond N, or molecular nitrogen, which is the world's best leaving group, and so it escapes. That's why nitrogen compounds are explosive. So we're going to make this give out its nitrogen and leave this dicarboxylic acid anion, and that energy, the release of the nitrogen, produces electronic excitation energy, and this happens to be a luminescent molecule itself. It fluoresces with the energy created by the chemical reaction, and it gives out light at a wavelength of 424 nanometers, which is on the blue side of green. So we're going to make a chemical reaction give out blue light. And while Rolf is coming up, I'm going to become a chemist for a few minutes. And luckily, I have a real chemist holding my hand, so when I make a mistake, he will make sure that we do not have any accidents. But as we showed the school pupils today, a good chemist must take protection. And so we are protecting ourselves with coats and gloves and safety glasses to do this experiment. And when we're ready, we will have to turn the lights out, so it'll be completely black for a few minutes, and I just warn you of that, but the chemical reaction should give out enough light for us to do it. Should we take it to the middle? What do you think? Right across? I just need to get these gloves on, which are made for children, I think. So, please excuse the delay. And my safety glasses are also suffering one of the weaknesses that plastics suffer. They're starting to crack, but at least I can see a little bit through there. So, Rolf, shall we switch across here? Shall we go into the middle? What do you think? Or is this okay here? What do you think? Can everyone see this? This is what you have to watch. No, you can't. Okay. We go right to the edge, and then we'll fall off in the dark. Now, okay? Oui, madame. Okay, so everything is mixed. We just need to now ask the lights to go down, and then we will turn the laptop off, but I need to... Okay, that would be lovely, Alan. So just the black square... Oh, I've taken the slide changer. It's over here. Yeah, wait, let me grab the flask before you do it, because I don't want to pour it down Rolf's trousers. Yeah, it's the one on the right, the square on the right, yeah. So we're ready, and you're going to hold the funnel too. Okay, Alan, if you do that, let's hope we don't miss. And this is the chemical reaction I showed on the slide, and it gives this beautiful blue luminescence. And once we've added everything, Rolf will shake this and show you the beautiful light. It's enough to, as I showed on the slide, the efficiency is 1%. That means 1% of the chemical energy released is being converted into light. And the solid state, is that? No? This one. Okay, that's the hypochlorite, right? Yeah. So I'm going to let the strong man pick up the 2 liters of beautiful luminescence. Let's put that back. And now the trick is to add a little bit more of the solid potassium ferricyanide, and you'll see that actually we're going to do a bucket job here, so it might just get out of hand. So let's see. And there you see the solid doing more oxidation and producing more light. Now, Rolf has the killer experiment, which is to add an oxidant like bleach to this. And this is the bleach, is it? Yes. We had a practice with the school children, and we mixed the wrong chemicals. So we nearly had a disaster. Now, this is a much stronger oxidant, and so it'll get bright quickly and then die. And isn't Rolf a wonderful chemist and a wonderful colleague for me to help? So let's give Rolf a round of applause for that. Thank you, Rolf. Thank you.
Thank you.
And we have had some fun practicing this. He does this experiment for the school children in the Chemiscope, which is in the University of Geneva. And it's a very successful event. So thanks. Thank you, Rolf. And I will see you later in the week to say thank you. Much appreciated. Now, that's chemiluminescence, and that phenomenon has actually been exploited very elegantly by chemists from Cyanamid, the American Cyanamid company, a man called Ed Chandros, who went on to head Bell Labs' research division, the electronics division. And what Ed found was that you could take that technology, and I need to show it here, you could take that technology on into a chemical reaction. And this is the chemiluminescence of materials called Cyalume, that's the trade name, or the Lumica light. light sticks, and I'm sure many of you are familiar with this. And I think this is a fantastic invention because there aren't many sources of light that are really safe. Torchlight is fine, of course, battery. And when I was in 1,000 Oaks in 1994, there was a terrible earthquake there in California, and the lights all went out in the hotel, and a lot of people walked around with their laptops for torches. So that's another source of light. But I want to demonstrate this light stick, and let me demonstrate that we have a fluorescent material in these light sticks. So the chemical reaction is one in which we start with an oxalate ester, and we oxidize it with hydrogen peroxide, and that does a reaction which essentially joins these two oxygens up and gives you this highly strained four-membered ring. In chemistry, small rings are usually highly energetic. And if you look at this molecule, this is actually two molecules of carbon dioxide joined together. So going from a strained small molecule to two molecules of carbon dioxide releases a lot of chemical energy, which is excitation energy, which electronically excites a fluorescent molecule which is stuck in the light stick and gets excited. So this is how these work, and I'll just get myself ready again to put the lights down to demonstrate this. So I'll start over here. So here I have a light source, and again I need the right safety glasses to stop damaging my eyes with this light source. I won't point it at you. So if we could go down with the lights again. And so here I have a red fluorescent dye in this light stick, and I want to demonstrate that just by shining the light source on the light stick. And you can see that is making the red dye fluoresce red just by the photoexcitation. So that's photoluminescence, electronic excitation by photostimulation. And we'll leave the lights down still, but I want to now demonstrate that with a blue light stick with a stronger ultraviolet light. And see, this is almost transparent, this tube, but if I now irradiate it with ultraviolet light, it will fluoresce in the blue. And you can see that. Very strong blue fluorescence. By the way, the whitener in this white shirt is also a blue fluorescent material, much better actually than the blue in this. So that's how we can do the lights up. That's how these work. And so you won't be surprised, and by the way, the green one there's a green one here that fluoresces in the green. So red, green, and blue, the primary colors of the visible spectrum. If we crack these light sticks, and I'm going to pass some around for you to take home or share with your family. There's the red one. There's the blue one. The chemical reaction takes place, and the fluorescent dye fluoresces red, green, and blue. I need some help from you, Ralph. We can pass some of these around. They're the blue ones. You can distribute some blue. I'll distribute some red and green. We'll just go randomly up the audience. And you can pass them round. One for you, certainly. Which would you like? Blue, yeah. Well, blue, red, and green. Oh, well. Since you're a star performer, I'll give you all three. That'll deprive them. I'll just pass some of these around. Okay. Now, I'm running short here, I hope. I'll get you to pass them around. And thank you. Rolf can do the rest. And the question, the interesting thing is that these sticks will last about 24 hours. But if you put them in the refrigerator, they will last much longer. And so the question I asked the school pupils today was to explain why that is the case. So there's chemiluminescence, quite good. Now what I'm going to start talking about, and we can come up with the lights now, thanks. And is that all right for seeing the slides, the intensity? Yeah. So I'm going to now move on from chemiluminescence to electroluminescence, and to talk about the discovery of light-emitting polymers. Now, this can be done actually with small molecules as a thin film, or with polymers, which are plastics. And this was a discovery that took place in the labs in Cambridge, actually in the physics department, in a collaboration between our group and the physicists in Cambridge. It was one of the early collaborations between physics and chemistry. Now it's common, but then it wasn't very common. And the discovery was that Jeremy Burroughs, who was the researcher who did the experiment, made a thin film of a conjugated polymer. So conjugation means like polyunsaturated. Single, double, there's single, double, single, double, single, double. So there are fewer hydrogens in the molecule than would be needed to make it saturated. And we call that conjugated. And this repeating unit, a polymer, because this repeat unit is repeated up to 50 times or more, is a fluorescent polymer. And it fluoresces in the green. So we have a thin film of this polymer deposited on glass on which there is a transparent electrode, indium tin oxide. So indium tin oxide on glass, the thin film of the fluorescent polymer, and then on top is a good negative electrode like aluminium or silver or magnesium or calcium. So this is connected to a battery, and the blue here is the silver electrode or magnesium. That is connected to the negative terminal of the battery, and the indium tin oxide is connected to the positive terminal of the battery, and the polymer gives out light, green light, because it's a green fluorescent polymer. So this is how it works. I explained already photoluminescence to you, or fluorescence. That is when we photoexcite an electron from the highest occupied level to the lowest unoccupied level. We photoexcite an electron. Here is the photoexcitation, if you like, kicking the electron upstairs. That's the singlet excited state, and it relaxes to the ground state by emitting a photon. In the case of polyphenylene vinylene, that is green light. Now, in electroluminescence, you can think of that as a plastic sandwich. And the filling in the sandwich is the fluorescent material, and the bread is the electrodes. So we connect it to a battery, and at the negative terminal, we force an electron in to the first empty level, which is the LUMO. That gives us what we call a radical anion. And at the contact with the positive terminal, we take an electron out, which leaves a positive charge. We call that a radical cation. And in this thin film, which is between a strong electric field, the charges hop until they meet each other and kill the charge and give the excited state, which gives out the photon of light. So we're making the film luminesce by electrical charge injection. So here's another diagram explaining that. Just the same configuration. Transparent positive contact, the anode, the polymer film in the middle, the negative contact on the top, the charges negative forced in from the top, positive forced in from the bottom. They hop through the film, and when they meet, the charge annihilation causes excitation, and out comes green light. That's electroluminescence. Fluorescence induced by double charge injection. So that happened in the early 1990s in Cambridge, and it was one of those situations where only we knew about it, and no one else knew about it, and we had about 1 year to discover and patent and protect and work with a secret that no one else knew. And over the years, we made a green fluorescent polymer, that's PPV. We showed that you could tune the color of the light emitted by making what we call a block copolymer, a statistical combination of 2 building blocks or more, and the light that you get out is the average of the wavelength that would normally be given by each individual block. So the weighted average of the combination of the 2 blocks controls the emission. And that's actually at the core of all the technology for tuning the wavelength of light emission. That was the chemist's very big contribution in this field. And we made high electron affinity polymers, which meant it was easier to push the negative charge in, and they happened to be red. And the so-called holy grail of the field was the polyfluorines. Blue light is the highest energy light, and so it's the hardest to attain because you need to have a material which has a high energy gap because it's blue, and yet you need to force the charging. And green, as you saw, those of you who've got the light sticks, you can see the green much better up there than you can see the red or the blue. The eye sees green much better than any other color. But there we have green, red, and blue. And as I've explained, and as I said already today to the school pupils, if you have red, green, and blue, you have the full spectrum of visible light for making color TVs. So we got quite excited about that. And we formed a partnership. The polyfluorine became the workhorse because you can use that as the core blue light, and then you can tune the color down to green and red. So that's been a core material in the technology. And we formed a partnership with Seiko Epson. Many of you know about Seiko, even in Switzerland, for timing, and many of you know about Epson for inkjet printing. And it's the inkjet printing part of Seiko Epson that was a very exciting collaboration. And you can think that if you look at a color screen of a TV with a lens, you can see little red dots, you can see green dots, and you can see blue dots. The eye doesn't see the dots when you stand back from the screen, so you get the eye averages and you see the full color image. So wouldn't it be good if we could print a color TV by printing red light-emitting polymers into one pixel or one cell, green ones next door, and blue ones there. And with Seiko Epson, that was done. And later on, in about 2004, they made a 40-inch, let's say 90 centimeters diagonal, full-color, flat-panel display by inkjet printing of light-emitting polymers. Now, actually, there are four equal, 1, 2, 3, 4. 4 equal areas. We call that tiling, and that is how they achieved a large area. So this looked very exciting, but there are two things in marketplaces. One is the existing technology, and the existing technology is what's in laptop screens, which is is liquid crystals. And there were new technologies coming on, like plasma, and then this one, which had to complete and displace them. In addition, as I said, you can get light emission from small molecules by evaporating a thin film of a small molecule, and you can get the same technology. And that's the one that's gone further into the marketplace. But it's still a technology which it has great opportunities. So it started with Philips. They put a yellow light-emitting polymer on the front of the phone to tell you there was a new message. Inside was liquid crystal. And then with small molecule devices, Pioneer had the very early technology for a car radio. Professor Kido gave me this car radio. Professor Kido is in Yamagata, where Pioneer have their main fabrication line. And this cost in Japan, when it was released, $600, because red is very hard to get, so it's just blue and green with the small molecule technology. But as Professor Aida will confirm, Japanese have a great skill in getting a new technology into the marketplace by introducing it and letting the public get excited, even if it's quite expensive. Sony and Sanyo also made small molecule full-color displays, and Motorola used a small molecule phone. Then along came Sony with a flat-screen TV. This was in about 4 years ago, 3 or 4 years ago, and this is a 10-inch diagonal, and the price, this is in California, this demonstration, $2,500. So quite an expensive flat-screen TV, but you can see here in this picture how thin it is, really thin. And then the really big breakthrough happened in the Las Vegas lighting show, Las Vegas electronics show in January this year, at the Consumer Electronics, when 2 Korean companies produced 55-inch organic light-emitting displays with small molecules, not with polymers. And this is really spectacular. You can see how thin it is, and you can see the brightness and contrast of the color. That's from Samsung, and this one is from LG. Lucky Gold Star was the old name for that company. They used to make toothpaste. Now they sell flat-screen TVs. And this won the award for the best of the show. These are not yet in the marketplace, but this technology from Samsung is the display. If any of you have a Samsung Android, it is this organic light-emitting display that is in the marketplace. Small molecule, not polymers. So, polymers might have their best advantage in white light. This is a polymer flat panel white light display, and you can make rather nice images by arranging the panels. And this is the polymer display, and this is the small molecule display. And the polymer people think this is better, but it's not yet in the marketplace. But you can imagine technologies where the whole wall is emitting light, and you can change the color by tuning which material gives out the light. So I thought I'd finish the bit on light-emitting polymers by showing you a movie. Now, this movie is a combination of various other movies. And it starts with a very famous movie called The Graduate in 1967. So many people here probably did not know of it, so that's why I'm going to introduce it. This film tells the story of a young man graduating from university in the United States. His name is Ben Braddock, Ben. And Ben returns home as a newly graduated student from the university, and his family hold a special welcome party. And Ben meets Mr. Maguire, who gives him some career advice. And the music is the music of Simon and Garfunkel. And then we switch to a television program made by the Australian Broadcasting Corporation, who came to Cambridge about 20 years ago and filmed some of our work. And finally, we finish with a news clip from the BBC television 20 years ago already, showing where this light-emitting polymer technology was going. So I'm now going to play that movie, and I owe a great debt to Professor McKinnon for telling me how to put a movie into the latest version of PowerPoint. Thank you. So I hope the light is good enough to play this, and the sound will go. So we'll just sit back.
Hello, darkness, my old friend. I've come to talk with you again. Because a vision softly.
What are you going to do now?
I was going to go upstairs for a minute.
Oh, I meant with your future, your life.
Well, that's a little hard to say.
Failed.
Ben. Excuse me.
I have no idea why.
Ben.
Mirroring. Thank you. We had lots of fun setting this up. What wonderful colleague to have Professor McKinnon here. It says turn off mirroring, but let's try again. This may be a disaster. My wife, who's a school teacher, says at this stage I should relate to all of you who are school teachers and know what happens when something goes wrong. So let's see what happens. If it doesn't show, we'll just have to skip it. Mirror displays. Thank you, Rod. Saved my day. I don't know what the display is going to look like now, but we'll live with that. Try again.
Hello, darkness, my old friend.
Well, something's going on.
With you again.
And I have no idea.
What are you going to do now?
We're going to have to skip that and move on to the next bit. But I'll just tell you what Mr. Maguire says to Ben. He says, Ben, I want to give you some advice. Yes, sir, says Ben. What's that? And he says, plastics. And Ben says, exactly what do you mean, sir? And he says, there's a great future in plastics. And this video showed Jeremy Burrows discovering light-emitting polymers. So that's too bad. At least we might get back on time. I apologize for that. So now, if you can put electrical energy into polymers and get light out, maybe it makes sense that you should be able to do the reverse and put light into a plastic and get electricity out, so reversing it. And we became quite excited about that and decided to develop that when I returned to Australia. So let's look at the world's energy demands. I think most people are very familiar with this story now, but the global energy demand in terawatts, which are million watts, is in 2001, this is electricity, I think this is electricity demand actually, it's 13.5 terawatts, predicted to be 27 terawatts. No, this is total energy demand, predicted in 2050. How are we going to get this energy when we all believe, I think, that fossil fuels are the source of carbon dioxide? Well, McKinsey analysts have predicted that various parts of the world, including Australia, should be able to make electricity from solar sources competitively with the cost of generating electricity from coal-fired power stations. And that is certainly true in certain parts of the world now with the best silicon solar cells. I thought I would share with you what I discovered from the statistics of the energy sources in electricity sources in Switzerland. According to these websites, Switzerland generates 54% of its electricity from hydroelectric sources, both running water and from storage dams, and 41% from nuclear power, meaning very little from fossil fuels. And here was the statistic as reported in this data in this website. So you see nuclear 40%, running water 23%, stored water 30%, and only a tiny amount, just about 6% from classical thermal power stations, probably coal-fired power stations. But I understand that Swiss government has made a commitment to reduce its nuclear power dependence, so there's a challenge also for your country to find energy either by buying it from another country or by using sustainable energy sources. Well, this is a map produced by NASA of the intensity of sunlight falling on the Earth's surface. And the browner the picture, the more intense is the sunlight. So you see Australia has a lot of sunlight. Even where I live, down here in Victoria, it's browner than up here in Germany, where Germany has invested a lot of money in silicon solar energy. So it makes a lot of sense, I think, to do some research on solar energy. And Australia does actually have a leading position in research on silicon solar energy. And nearly all the people who trained with Professor Martin Green in the University of New South Wales eventually went back to China and became very rich people selling silicon solar. A lot of Green's technology is in the silicon solar industry in China. So Nathan Lewis in Caltech says that if we could have photovoltaic generation at the efficiency of 10%, so 10% of the sun's energy being converted into electricity, which is easily achievable now with silicon. For example, just one area in this part of Australia, which is land largely owned by indigenous people, so it's not ours to use without their permission, 100 by 100 square kilometers. That's big, but you can imagine how big. It's not impossible to think of driving 100 kilometers. So an area of that size could actually generate at 10% energy conversion efficiency enough electricity for the whole of the United States today. And 6 of these in strategic places, and of course Europe is interested in drawing from North Africa, could maybe meet the terawatt gap between 2010 and 2050. So it's a very big task, but it's one that's within the conception of the human brain. And this is a good cartoon from one of the Australian local newspapers. We all worry about fossil fuels when we should be thinking of the solar system's best nuclear reactor. So we formed a consortium in Victoria, in Australia, in the southeast corner, which consists of the University of Melbourne and Monash, and the Government National Research Lab. It's called the Commonwealth Scientific Industrial Research Organisation, the future manufacturing flagship. This is a national research lab that has about 6,000 employees, that covers all the disciplines of science, from basic physical sciences to oceanography and marine and Antarctic science and biological science. And then our industrial partners, the company that makes steel roofs in Australia, a lot of buildings have steel roofing, and they would like an integrated solar cell on the roof. Bosch in Southeast Asia, they have a big business in silicon solar cells, but also in a startup company in Germany in organic solar cells. And this company on the left, which I want to illustrate now, and I might need to go over to the lectern. Are you looking at me here? Yeah. So I want to show you some Australian money. And it's made of plastic. You can't tear it. You can't photocopy it because it has a hologram and transparent window, and it has lots of electronic protection devices, and you can't destroy it. Now, I was demonstrating to the interpreter the weakness of Swiss money. I do apologize. I didn't mean to do it, but I was saying this is what happened when I was in China in April, and the Chinese banknote fell in half, and I could hear the air go. So I'm sorry to the Swiss citizens. I didn't mean to destroy your currency. But this company knows how to print this money. It's a laminated polypropylene. It's a plastic, and it has long life, and it's a brilliant technology, and it's in about 30 countries around the world. Not in Northern Europe, or not in Northern Hemisphere or in the United States, but it's coming into Canada in the $5 banknote soon. And it's in many Southern American countries and Southeast Asian countries. So they know how to print on plastic. And the funding has come from the Australian federal government and the Victorian state government, and these are the individual departments. So we have nearly $15 million of funding for this, and this consortium is working collectively on the whole aspects of synthesis, device fabrication, printing, and encapsulation to stop the device degrading. So remember I showed you this luminescence slide, and I said that when you photoexcite an organic molecule, it usually wishes to relax to the ground state by fluorescence. Now, if we're going to make an organic molecule into a solar cell, when it's photoexcited, it must then charge separate. And organic molecules don't like that. They would rather fluoresce or give out heat. Now, nature has found how to solve this problem with the photosynthetic receptor, but of course it doesn't generate positive and negative charges. It generates, what does it generate? It oxidizes water to oxygen, and it reduces carbon dioxide and forms carbohydrates, so it makes chemical molecules. So it does it by playing a trick in terms of spatial separation of the cascade so the charge can be extracted. And that's the trick we have to play with organic solar cells as well. So the way we do it is we make what's called a bulk heterojunction solar cell. And bulk means a lot of material. Heterojunction means two different materials, and let me explain it. So I'm going to demonstrate a solar cell in which the substrate is plastic, the same plastic as is used for drinking Evian water. Well, it's not Evian tonight, but this bottle is polyethylene terephthalate. So that's a cheap plastic coated with a transparent electrode called indium tin oxide. And then we have a flattening layer, like a leveling compound, to level out the spiky electrode. So indium tin oxide, a leveling conducting polymer, and the active layer, which is a blend of a conjugated polymer, polythiophene, the donor, and an acceptor, which is a fullerene or a buckyball. So that's the heterojunction, the donor-acceptor blend, and then a top electrode to take the positive charge out, the negative charge out. So solar cell efficiencies, that is this term, are measured by the product of the short circuit current, the open circuit voltage, and the fill factor, which is the actual power relative to the theoretical maximum produced. So we want each of these numbers to be as big as possible for a good solar cell. And so this is the bulk heterojunction. We have a blend of a donor material connected to this electrode and an acceptor material connected to that electrode. And the idea is to have this surface area between donor and acceptor as large as possible, because the photoexcitation in the donor must generate an excited state which must move to this interface where the charges are pulled apart into the donor and acceptor within 10 nanometers. Otherwise, it will fluoresce or give out heat. So you want a perfect blend, and people think this geometry might be the best, this interpenetrating network of donor and acceptor polymers. But it's quite hard to make that in the laboratory, although in Japan, the Mitsubishi company has recently done that. So the best results for polymer solar cells with a buckyball, a fullerene, 8 to 10% on a tiny cell, 10 postage stamp size. With polythiophene and fullerene, you can get about 5%. And with small molecules, again, the small molecule competition with a startup company in Germany called Heliotech, partially owned by Bosch, partially owned by BASF, is at 10.7%, but that's a tandem cell with two cells back to back. So that's where the technology is in the marketplace. And we have used molecules, I'm not going to talk about them, called hexabenzochoronenes as the donor material because they stack. And actually, Professor Aida was the person who demonstrated how beautifully these molecules can stack. So the better the stacking, the better the order, and the better the charge extraction is. So you need a supramolecular ordered material to get the charge out, and the fullerene also has to order itself. And our collaborator in Ulm is Peter Beuerler, and he has helped us decorate these hexabenzochoronenes with light harvesting branches, like the dendrimers that were spoken about by Professor Aida. And Professor Beuerler likes the Australian beer called Foster's Lager, and this is the symbol. And this is an Australian surf life-saving boat at Lorne, where both Professors McKinnon and Ramakrishnan have been for protein chemistry conferences. So this is on the beach. And in the old days, the lifesavers would row this boat out through the surf to rescue people. Now they use a much more modern motorized dinghy. But here's Beuerler, here's Foster's Lager. Of course, he was there for the science. So I'm going to skip through this because we're running out of time. But if we're going to print solar cells, we need to make large amounts. And so we're making large amounts by continuous flow chemistry. And this is called a vapor tech. And we can run this for 24 hours, continuously making, for example, the fullerenes that we use. Here are the fullerenes. This is PCBM. This is another fullerene. And we make them by continuous flow. And let me just show you the result. So if we make it by flow chemistry in 100 minutes, we can make the same amount as it takes 22 hours in batch chemistry and in the same yields. And so in one day, we can produce 15 grams of this material, and that's large enough to print 1,500 square meters of a printed solar cell, which I shall show you. So we can now make large enough amounts to use for printing. And here's our printer. This is called gravure printing. This is a mini labo printer. And it's actually, I've got a film of the print that's being used here. This is the polyethylene terephthalate with indium tin oxide. And there you see the blend of the red poly-3-hexylthiophene and the fullerene printed on this. This is exactly printed on that printer. And this will be a solar cell when we finish it off with one more electrode on top. So that's how the solar cells are printed. I need to put on the power to illustrate this in a minute. And so that's the film I showed you of the printed polymer film. And needs just one more layer of electrode to make a solar cell. So we can print this, and as I said, with that fullerene, we can print 1,500 square meters of that. So we first printed with just a rotating proofing press. Then we used this mini labo press. This is where the Australian money is printed, and they won't let the photographer get any closer to see the technology. This can print at 300 meters a minute, very fast. And this is spray deposition. Now, I have another movie, which I hope to show you, which I hope works to illustrate the printing. So this is one of our fully printed solar cells. That's the roll you saw. The state of the art on small cells is 8 to 10%. A competitor company is printing 4%. We are not quite there, but we are printing, and I've brought some of the solar cells with me that we no longer use, but you see it's fully flexible, and that's our typical module size, 10 centimeters by 10 centimeters, and they work quite well. And I think I'm going to just demonstrate that on the device here in front of you. But before I do that, the Konaka have put the poly-3-hexylthiophene solar cell on the roof of a bus shelter in San Francisco, and they use the solar cell to generate light for the bus shelter and to tell you the time. So there you see the solar cell. It's the corner of Geary and Arduello, if you know San Francisco. So before I finish, I'm going to demonstrate one of these printed solar cells. So this is a fully printed solar cell. We'll have to switch it over. What do I do? It should be on the camera. Why isn't it? He has to switch it over. That's right. And then we have to come back. So instead of the sun, I've brought a rather powerful light source. And this is the printed. This is one like these. It's still working. Fully printed, completely. Everything's been printed here. And I just need to get the light onto it. Get it going, and then So that's just simply... Now, that solar cell in Oxford in February this year, inside, was working in the weak sunlight. So these organic solar cells are more efficient at low sunlight than our silicon solar cells. And that's illustrated by how well they work just with ordinary light, white light from this source here. So if we can now go back to the video, I hope my final movie will work. Can we go back? Yeah, to the laptop, please. Thank you. So, before I finish with the movie, which I hope will work, showing the printed solar cells, I've talked about conjugated polymers, light-emitting polymers, printing solar cells, and I think it's important to finish by reminding ourselves that most of the way in which science is discovered is by serendipity, and that's what makes it so exciting. And I think I've illustrated that it's also about doing things at the interface of more than one scientific discipline. And as a chemist, I must say that it's a central science. It's central, and we can see that by two of our Nobel laureates who have been awarded the prize for doing science at the interface of chemistry with biology. And of course, the classroom is the way in which people are inspired to become scientists, and we praise the teachers for their great work. So let's see if this solar cell works. This movie works. I'm very nervous now. But this finishes with just showing a little bit about how we make solar cells and how we print them. And there is some dialogue at the end, but some of it is science. It's not involved. Sorry?
Polymer banknotes to polymer solar cells.
Yeah, I've been caught out by the technology which is not translating the movie to there. I could actually go and open a movie and show them, but that would take a while, and I think we may not have time. So what I probably should do is finish...
The aim of the research is to effectively make solar cells so cheaply that it's a logical choice then to use solar energy.
I can play the movies as separate movies, and that might be the best way, but I think the time is too late, and it might be better to keep them at the end for anyone who particularly wants to see them, rather than try and do it now. So I will finish with acknowledgements, and these are the people who've worked with us in Australia and our collaborators in various parts of the world, and we've been very fortunate to have many international partners. And this is the current research group in Bio21 Institute in Melbourne. So can I thank you very much for your attendance and for your interest in the lecture tonight.
Thank you, Andrew, for a very illuminating lecture. Now, as usual, we'll have a short break for people to hand in questions, which will then be discussed by the panel of all the speakers. And may I suggest that you don't only ask questions about tonight's lecture, but we've had lectures on biology, on materials, on energy. Any question that can be discussed by the panel will be welcome. Thank you. We have just a few questions. What about microelectronics? May polymers or eventually graphene replace silicon one day?
Can you repeat the question, please?
Yes. Yeah. What about microelectronics? Will polymers or perhaps graphene replace silicon one day?
Well, I think that we will see organic electronics in many applications. That's the first thing, microelectronics, and in this kind of nanotechnology that we'll hear from Professor Lee tomorrow. But specifically, graphene could be the solution to replacing the indium tin oxide transparent electrode, which is, indium is a very rare metal, and we will run out of indium. If we can print graphene as a transparent electrode, that will be a very important aspect. There's one other aspect of conducting polymers, which I think is the most exciting opportunity for the future. It's not our work, but it's the work of people like Professor Gordon Wallace in University of Wollongong in Australia, and that is to use conducting polymers to make junctions with nerves. And there's a lot of, for example, the cochlear ear implant, to use conducting polymers for the connectivity with auditory nerves and so on. And I think that's a really exciting area.
Now, the two questions here. Well, the first one, how far in time are we from artificial photosynthesis? How well do we understand photosynthesis anyway?
Well, I certainly do not understand photosynthesis at all, but what I see is that people trying to do artificial photosynthesis and absolutely replicate nature in oxidizing water and in producing carbohydrates have got a long way to go. And to my mind, and I'd be interested in hearing my colleagues' views on this, the most useful thing we have done in learning from photosynthesis is to use the porphyrin, which is the generic structure of the light harvesting dye in photosynthesis in organic solar cells. And in fact, the Japanese solar cells, the Mitsubishi solar cells, use an ordered porphyrin as the light harvesting dye, and their efficiency is in excess of 10.8%. So that's the most important thing I think we've learned from photosynthesis, but I bow to views from my colleagues on this.
Perhaps I could make a comment because it's a little bit in my field. I think that we understand photosynthesis quite well, but we can't imitate it. But you have to remember that nature took 2.5 billion years to work it out for itself. So I think we could ask for another month or two.
We're just asking for the 40 years that silicon has already.
Another question, this is perhaps for everybody, how do you see the future in terms of collaboration between biochemists and physicists? What would you like to see the physicists do more? I guess that's addressed to Rod and Venki, I don't know. Well, you are a physicist, Venki, yeah.
So perhaps I can speak as an ex-physicist, because no physicist today would consider me one of them. I think physicists need to... Physicists have great skills. They understand fundamental concepts. They have a very high level of quantitative and mathematical skills, and they have terrific skills in instrumentation. I mean, we just saw an example of that when we visited CERN today. What physicists often lack is humility, okay? They feel that they're somehow at the apex of a pyramid, and that, you know, they just need to sort of pontificate from upon high, and everybody ought to learn from them. And it doesn't work that way. There are many physicists who have gone into biology and done absolutely nothing worthwhile. And there are other physicists. Max Delbruck was a classic example of a first-rate physicist who went into biology, but other people like Francis Crick, who were not perhaps top-notch physicists, but who went into biology and learned biology and became effectively biologists and understood the problems. I think those went on to do rather good work. So I think there has to be some level of understanding that different problems have different scales, that because your science is more fundamental doesn't mean that you automatically understand things in more complex systems, and you have to have some sort of mutual respect and understanding. And if that happens, then I think, there could be tremendous collaborations. I worked for many years at Brookhaven National Lab, which was dominated by high-energy physicists, and I have to say there was very little interaction, in my 14 years there. Okay.
Yeah, so I guess I'd just add to that I think many of the traditional divisions between disciplines of science are becoming less and less relevant today because science, the problems we're facing today by nature are much more interdisciplinary. Many questions in biology require people with quantitative backgrounds, and I just think the distinctions are definitely being blurred, and so that I think, I just think the traditional divisions actually don't hold very well anymore for many branches of science.
Okay. Somebody asks here, solar cells, what's the relative yield compared to silicon? Are they similar or very different, and price also, I guess?
So this is an important question, but I don't think it's... that's where the 40-year answer comes in. So the best silicon solar cells, which are often... and best solar cells, which are two layers, are tandem cells, so you get more of the solar spectrum. The ones that are in space, they're in the high 20s to 30% efficiency. The ones you buy for commercial domestic activities range between 10 and 15% typically. Some are a bit higher, depending on whether they're amorphous silicon or crystalline silicon. Our printed solar cells, and remember I can print 1,500 meters before silicon can turn on the furnace, are 2% efficiency, but we will get there, and people are talking about aiming for 10% efficiency probably by 2020.
Your last question?
Yeah, I had a more general question, which is about the economics of solar cells versus fossil fuels. Until recently, it looked like we were running out of fossil fuels. And of course, fossil fuels have this problem of CO2 emission. And, but what has happened recently is the discovery of other sources of fossil fuel, especially shale oil. And there are predictions that the US will be essentially self-sufficient in energy using shale oil and shale natural gas. And so there's a worry, and I want to know what you think of this. There's a worry that people simply will stop investing in solar technologies and things which we really need over the very long term.
I agree with that, and I had to organize in Oxford in March this year a symposium as part of my appointment, Can Renewable Energies Deliver? And a very senior person who had served in government said that they thought the only country that would deliver on the 20% renewable target by the 2020 would be Germany, and that he thought that Britain would switch to gas as the solution, as you have suggested in the United States. And the worry is that people will believe that because it's more efficient, they've solved the greenhouse gas problem. Silicon at its best is now about $1 per kilowatt installed capacity. So that means for 1 kilowatt you pay $1,000. And the price of silicon is in places like Spain and certain other parts of the world where there's a lot of sunlight, is delivering payback time in about 2 years, and at the price without subsidy,
well, of course there is subsidy, but there's subsidy in coal-fired power stations everywhere and nuclear. But without subsidy, silicon will produce electricity at about the same price as one pays for thermal generated electricity in the best parts of the world. So it should work, but governments will have to invest, and if they don't, we will do exactly, I think, as you've said.
I have a question about kinds of solar energy. So how does the solar panel, photovoltaics, compare to a very simple approach to solar energy, which would be have reflective lenses that will boil water and run turbines?
This is a question being highly debated in Australia, where because we've had abundant fossil fuel, we haven't switched to solar well, but the solar thermal is by far in other words, a very big boiler heated up by sunlight is a very competitive way of providing energy to drive power stations. The only problem with all this is that none of these work when the sun isn't shining, and so you have to have some kind of capacitor, and I don't think that problem has been solved. Here in Switzerland, you pump the water back up with cheap nuclear power, but to my mind, the capacity problem, storage, even though most energy is required during daylight hours, that hasn't yet been solved. But that still doesn't mean that it won't reduce greenhouse gas emissions enormously. So the solar thermal is either concentrated on very efficient silicon cells with lenses, or for solar photovoltaics, or by generating hot water to drive mechanical devices, is a really important technology. And there's a bit in California going for it.
So there's a question here, I think, which may be related to that. Somebody said, is the competition in Africa with the Desert Tech project, which is German-inspired? I don't know if that's the same technology. But
I'm not sure if that's not the technology of bringing power from Northern Africa to Europe.
Yeah.
But also we were talking, a number of the organic photovoltaic companies, who of course have no marketplace, are quite interested in providing solar energy in developing countries. So in many developing countries, there is not enough energy for light at night. So simply providing cheap plastic solar cells that will generate a battery to run light for just simple illumination at night is actually a very attractive project. And probably even this technology is sufficiently good to work in that market already, even at that low efficiency.
So, somebody's taken up on what I said at the beginning. They said, if you need plastic, you won't be able to make these if there's no more oil, will you?
No, that's why we're keen to hold on to it for the use as fine chemicals. Of course, there is a very good syngas technology where you can produce from other fossil fuels. You can produce methane and then produce fine chemicals based on carbon. That was, of course, the Sasol process in South Africa and brown coal process in Germany. So we can use fossil fuels to make chemicals, but oil is awfully much better.
What's the lifetime of these photovoltaic cells?
The lifetime is poor. We are working very seriously on all those cells I showed are encapsulated. In fact, may I? Even this keeps air. This is a peanut package. So all our food is already protected from oxygen. So this is just aluminium deposit on polymer film. So this is not good enough for solar cells. I'm going to answer the question. Because the barrier properties are not good enough. And there are no commercially good barrier materials in the marketplace. And so the problem is that our most expensive component in our project is buying in research quantities of barrier materials for encapsulation. Now, at the moment, we're doing lifetime studies, and we have lifetimes of months in real weather conditions, 60, 70 degrees Celsius, 60, 70% humidity. That's accelerated lifetime testing. But Heliotech have 2 years lifetime in their best cells. Of course, to get real lifetimes, not accelerated times, you have to wait till you get them. So that's why accelerated testing is good. Our cells are quite short-lived at the moment, but we are doing work, and not many others are doing it, on the barrier materials, and that's a really important area. But it's not exactly the kind of project that a really enthusiastic chemistry PhD student wants to work on. It's a very applied problem and should be probably done by government agencies. Can I just finish by saying that polymer, light-emitting polymer display that I showed, I did put it on. I didn't.
No, you forgot to.
When this technology was first developed, we showed the dean the technology, and I remember him saying, "Oh, very interesting," and I knew there was no light there already by the time he looked. So what I'm saying is the first light-emitting polymers lasted seconds. Now, with the careful fabrication, careful purification, integrated manufacturing, clean room technology, encapsulation technology, they have lifetimes of hundreds of thousands of hours. So I think solar will get there. The encapsulation will give us the lifetimes, but we're not there yet.
Somebody asked, in what way could we combine aqua materials and printed solar cells?
I would love to have a collaboration with Aida-san. So I think that the interesting question is whether we can make them semiconducting.
Some years ago, I was told in Japan about folding screen technology. Is this still an option?
Can you help me with what we mean by folding screen?
I just have the question.
If we mean roll-up screens, certainly, eventually. Flexible screens, certainly. But at the moment, it's not in the marketplace. But that's the vision of all these companies with the flexible luminescent displays, is to have a flexible roll-up screen.
Okay, perhaps one thing to finish. You've probably noticed that you've had American English, Australian English, Japanese English, and I would like to thank the interpreters, who I think are up there, for making you understand this.